Hi, it's me, Dr. Prasad Puthiyillam. Continue my classes on coordination chemistry, that is magnetic properties of coordination compounds. In previous class, explained about the orbital contribution to magnetic moment. It's a continuation of that. How to calculate the magnetic moment, mainly the spin-only magnetic moment of coordination compounds. Okay, magnetic moment mu, it is measured in terms of Bohr magneton, and it can be defined as one Bohr magneton is Eh upon 4 pi mc, in which E is electron charge, H is Planck's constant, m is electron mass, and c is velocity of light. In case of calculating that of coordination compounds, the magnetic moment calculation, the magnetic moment may arise due to the spin of electrons and orbital angular momentum, where S, that is the sum of spin quantum numbers of individual electrons, which is calculated as number of unpaired electrons in the system multiplied by spin of electron. Spin of electron is half, and L is the sum of orbital angular momentum quantum numbers, that is L. Okay, we know how to calculate L. It may be dependent upon number of L plus 3 plus 2 plus 1, like that. So coming classes will take the examples and I'll explain in detail. So if only spin of electron is considered for calculating the magnetic moment, then it will be called as spin only magnetic moment. The expression to calculate spin only magnetic moment, mu s, is equal to g multiplied by square root of s into s plus 1 Bohr magneton. Here g, which is known as a constant gyromagnetic ratio, which is approximately equal to 2. So if you consider the g value as 2, substituting the in place of g, you'll get mu s is equal to 2 square root of s into s plus 1 Bohr magneton. Taking the 2 inside the square bracket, square root, it becomes square root of 4s into s plus 1 Bohr magneton. Here s, that is the number of unpaired electron multiplied by spin of electron, that is half. So substituting that value, it becomes mu s is equal to 4 multiplied by n by 2, and in bracket n by 2 plus 1. On rearranging it, it becomes mu s equal to square root of 2n n plus 2 divided by 2, cancelling the terms 2, or cancelling the 2 here, we'll get n into square root of n into n plus 1. Therefore, spin only magnetic moment can be easily calculated as square root of n into n plus 2 Bohr magneton, in which n, it is the number of unpaired electrons. Therefore, in a given coordination complex, if you draw the orbital splitting, crystal field splitting electronic configuration, we can see how, we can check how many number of electrons, unpaired electrons are there. If you know the number of unpaired electrons, the spin only magnetic moment can be calculated very easily. Okay, therefore mu s is equal to square root of n into n plus 2 Bohr magneton. If the number of unpaired electrons is 1, okay, we are not taking any example as such. Say here only, if we substitute n equal to 1, then it will get 1.73. It becomes 1 into 1 plus 2, that is 2 plus 1, 3, 3 square root of 3, like that we can calculate. If number of unpaired electron is 2, the value will be 2.83. If number of electron is 3, 3.87, so on. For number of unpaired electron is 5, then it becomes 5.92. So let us take some examples. Okay, the movement of electrons around the nucleus. Okay, the motion of electrons around the nucleus may, in some materials, give rise to an orbital moment, which contributes to the overall magnetic moment. That means not only spin is considered, even the orbital moment is also considered. In case where the orbital moment makes its full contribution, if the orbital moment have got full contribution, then spin only formula cannot be used. We have to use another formula. Mu s plus L is equal to square root of 4s into s plus 1 plus L into L plus 1, where L is the sum of the angular orbital momentum, that is small letter L. It's a summation you have to take. So calculating the magnetic moment, the spin only magnetic moment, with some examples. Say a complex Mn F6 4 minus. First we need to find out what is the oxidation state of Mn, manganese here. So let us take it as X. Okay, manganese has X, and F has got a -1 oxidation state, therefore 6 times, and it is totally equal to 4 minus or -4. Therefore X is equal to +2, or we can say here Mn is in 2 plus oxidation state. So electronic configuration of Mn, we know that is argon 18 argon electronic configuration, continued as 3d5 4s2. If it is Mn2 plus means 2 electrons are less compared to the electronic configuration of Mn. It becomes 3d5. 3d5 means it is a d5 system. So the given complex is a d5 system. Now the nature of the complex, if you see, nature of the ligand as well as whether it is tetrahedral or octahedral complex. We know that 6 ligands are there, therefore it is octahedral complex. And F fluoride, halide, it is a weak field ligand. Therefore the given complex is an octahedral complex and the ligand F minus is a weak field ligand. Therefore pairing electron is not preferred when we arrange the electrons. Since it is a weak field ligand, there is no compulsion of a pairing. There is no charge, negative charge, which forces the electron to undergo pairing. Therefore, we already see in previous class the crystal field splitting in octahedral complex. It split into EG and T2G stages. So for D5 system with weak field ligand, pairing is not forced. Therefore, 1, 2, 3, 4, 5. So unpaired electrons. So we can say this is a high spin complex situation here. The number of unpaired electron here is 5. So all the 5 electrons are unpaired only. Therefore, we can calculate the spin-only angular magnetic moment mu s as square root of n into n plus 2 Bohr magneton. Substituting n as 5, it becomes square root of 35, that is 5.92. One more example, if you take iron Cn6 4 minus, first we need to find the oxidation state of the central metal ion, that is iron. Oxidation state of iron here is x plus, so we took it as x, the oxidation state of iron. 6 into minus 1 cyanide has got minus 1 oxidation number. 6 into minus 1 equal to 4, therefore x here also becomes plus 2. Therefore iron is in 2 plus oxidation state. The ground state electronic configuration of iron is 3d6 4s2. When it loses 2 electrons, it becomes Fe2 plus ion. Therefore Fe2 plus is 3d6 system. Therefore it is a d6 system. Given complex is a d6 system. Now the complex, the nature of the complex, cyanide, it is a strong field ligand. 6 times cyanide is there, that means it becomes almost octahedral complex. Therefore it is an octahedral complex. The ligand is a strong field ligand. In presence of strong field ligand, when we write the excited electronic configuration or the ligand field electronic configuration, if you write, pairing is preferred because the cyanide is a strong field ligand. Therefore, for D6 system with a strong field ligand, we can write the electronic configuration as 1, 2, 3, 4, 5, 6. Therefore, it is a T2G6. Electronic configuration is T2G6 EG0. Okay, therefore, it is a low spin complex situation. Number of unpaired electron is 0. Therefore, in a spin only magnetic moment, if we calculate n equal to 0, that means total value becomes 0. One more example, if you take FeH2O 6 times 2 plus, let us calculate the oxidation number of iron, X plus 6 into 0. Here water, it is a neutral ligand, there is no charge on there, therefore 0, therefore X is equal to plus 2. Therefore again F is in 2 plus oxidation state. The ground electronic configuration of iron is 3d6 4s2. Iron 2 Fe2 plus is 3d6, is a d6 system. Whereas the nature of complex H2O is a neutral ligand, or say, you can say it is a weak field ligand, there is no charge as such. Therefore, pairing electron is not preferred, and it is an octahedral complex. Therefore, let us the electronic configuration. So pairing is not preferred. So 5 electron, 6th electron will undergo pairing in T2G. Therefore, we can say it is T2G4 EG2 system, or T2G4 EG2 is the electronic configuration of this complex. It is a high spin complex. Number of unpaired electron is 4. You can see unpaired electron 1, 2, 3, 4 unpaired electrons are there. And if you calculate the spin only magnetic moment, it will be substituting n as 4. It will become 4 into 4 plus 2. That is square root of 24. The value is 4.9. Okay. Therefore, we can conclude that we can calculate for all the possible complexes with vanadium, copper, with possible oxidation states. So vanadium 4 plus, the number of unpaired electrons when we check it in case of octahedral complex, it will be 1. The first spin only moment is 1.73. Copper 2 plus, again unpaired number of unpaired electrons will be 1. 1.73 will be the spin only moment. Vanadium V3 plus, 2 unpaired electrons are there. 2.83 will be the spin only moment. Nickel 2 plus, 2 unpaired electrons, and 2.83 is the spin only magnetic moment. Cr3 plus, chromium 3 plus, 2 unpaired electrons are there. 3.87 is the magnetic moment. In case of cobalt 2 plus, If it forms high spin complex cases, 3 unpaired electrons will be there. Therefore, spin only moment will be 3.87. Cobalt 3 plus with a 4 unpaired electron high spin situation, 4.9 will be the spin only magnetic moment. Iron 2 plus with a 4 unpaired electron in high spin situation, 4.9 is the spin only moment. For Fe3 plus 5 unpaired electrons in high spin situation, 5.92 is the spin only moment. With Mn2 plus with 5 electrons unpaired electrons in a high spin situation, we'll get the magnetic moment as 5.92. Okay, so that's about for this class, how to calculate the magnetic moment. So you can calculate, you can check it for all possible coordination complexes. The spin only magnetic moment you can calculate, but in some cases the spin only magnetic moment what we calculate theoretically, the observed magnetic moment will be different. That will discuss in the next class. So once again, thank you very much for watching and have a nice day.